So good morning, everybody. My name is Sonal. I am a distinguished engineer at Xilinx, and I've been working on FPGA acceleration for the last 5 years. I'm going to talk about XRT, which is the acceleration runtime built by Xilinx. And the X in XRT stands for many things like scalable, flexible, acceleration. It doesn't really stand for Xilinx, X as in Xilinx. So here's the agenda. I want to talk about the overall architecture of XRT, some of the key tools that we ship along with XRT, how do we do cloud deployment, because we are deployed in many hyperscalers today, the security model of XRT, and the open source engagement and development that we have been following for the last 1 year. So XRT architecture, I'll skip this slide. I'll first go here because this is the overview that we need first before we look at the XRT in detail. So for any acceleration offload, an application has two parts. The part that goes and runs on the acceleration device and the part that will run on the host. So in this picture here, you can see that if you are accelerating for Xilinx devices today, or even think of it like GPU or any other architecture, you'll use a target compiler, which in case of Xilinx is called V++, and you can use C++, Verilog VHDL if you're hardware savvy, to compile your design into a.xclbin. That's what we produce. Or for the host code, you can write in C++, compile with G++, LLVM, whatever you like. Or if you want to write in Python, we have a first-class Python binding for XRT. All of this is where XRT acts like a glue and then starts providing the services of the device in an abstracted fashion, and including things like, now if we go back to this slide, what is XRT? So XRT is a modular architecture with different layers performing different tasks, and it provides key services like device management, loading of images on the device, the memory management of the device. Now, remember, there are different classes of devices out there with PCI attached memory, with embedded device. Think of it like an ARM processor or some other processor embedded inside a hybrid device, which is plugged into a PCI host, or an edge device like MPSoC devices from Xilinx, which have ARM cores and FPGA all in the same chip. XRT also does the scheduling and execution, so it abstracts the concept of how do you do scheduling for multiple boards with multiple compute engines and in a secure fashion. So it's multi-process, multi-board, multi-compute engine capable. We support different kinds of abstractions at the top, which means you can run applications in OpenCL, or you want to do machine learning, or you want to write raw XRT applications in Python, C++. All of that is possible today. So all these solutions that you see from Xilinx now use XRT underneath. And XRT has a bunch of user space components and Linux kernel driver components. For PCI, there are two drivers because we are a multifunction device with two physical functions, and for MPSoC we have another driver called XOCL. So we'll touch upon this more as we go through the next set of slides. One key aspect of XRT is that there is one single API, the common API that works across all these classes of devices. So the same application you can recompile to target for edge, or you take it to a data center or enterprise, you use the same XRT APIs everywhere. So with that, let's look at the modular aspect of our drivers. So XRT has this, the drivers themselves are organized as a collection of platform devices, so platform drivers. So it's one driver, but inside that there are different platform drivers for different components or peripherals that you'll see in our devices. And that makes it very extensible. So if you have an extension of our device, you want to add some more peripherals, you add a platform driver to XOCL or XCLMGMT. And when I say XOCL and XCLMGMT, there are two Linux kernel drivers for all the PCI class of devices, which means if you take our Alveo boards and you plug it into a x86 server, ARM64 server, or PowerPC, you'll see these two drivers will show up. And they abstract the devices into a set of POSIX calls, set of custom IOCTLs, and a set of sysfs nodes. So that's how the drivers themselves are architected. And since it's a multifunction device, there is a mailbox, that hardware mailbox that's used for communication between these two drivers. The management driver is considered a driver with a lot of trust. So that usually is system administrator trying to manage the device. And the XOCL is a driver that the end users interact with. So here is a brief overview of the management driver. I'll not go into the details, but again, as I said, that this is a trusted component of our architecture, that if you are doing a virtualization, you typically hide this driver completely in the host. And the XOCL driver is what the end users typically interact with, and it does all the interesting things, like it has access to your DMA engines, the memory management that we talked about. You want to do buffer import, export, multi-process, multi-thread. This is the most interesting part of our architecture. And we have built-in support for different execution models. It's called, today they are called HLS because that's how we started. But like start-stop model, data flow model, all of those are supported today. So I'll not go into details on this. The XOCL driver is the equivalent driver like XOCL, but it's for the edge devices. So this is a more interesting picture where it shows that you have an application that you are targeting different classes of devices, whether it's PCI device or embedded device. You write your application in various forms, C++, you're doing video, then you use XMA as a binding for XRT. The keywords, in the pseudocode, the API calls are in bold, and they are classified with different colors. So the green color APIs are what you will do to interact with the device from the management perspective. Open the device, load my image on the device, open a context for me. And then the blue ones are the memory management ones, which you will do things like allocate buffers for me, map the buffer, or sync the buffer in a particular direction. Now, sync has overloaded meaning. When you have a PCI device, it might mean DMA to the device or DMA from device. Think of it like file fsync. And if it's a device where you want to explicitly handle cache coherency, you can, it's the same API for those class of devices. And for execution, we have two APIs called execBuff and execWait. ExecBuff is where you give a command object to the driver and queues them up and then starts running them in the hardware. ExecWait is how you wait asynchronously for a task to finish. So there's more detail on this in the following few slides, but it kind of gives you a overview of how a native XRT application looks like. If you want to write an OpenCL, then you will write it at the OpenCL level, but internally the OpenCL implementation from Xilinx is talking into calling these APIs. So talking about memory management, right, and that's an important part of the XRT technology because we have different classes of devices where, with different characteristics, with, as I mentioned, like PCI devices with their own DDR memory or HBM memory. If it's a unified memory architecture like our MPSoC devices with ARM cores and FPGA right as one chip, then we support, or XRT supports, the CMA allocation for contiguous allocation or SVM as part of our core architecture. You can also share buffers between the host and a device, an MPSoC style device, PCI hybrid device with its own ARM core embedded or plugged into a PCI host device. So you're basically sharing buffers between two processors, and we provide that abstraction very neatly. And of course, you can do things like PCI peer-to-peer transfer or DMA buff import, export. Those things are also built in. And there are some advanced concepts we have, like we do page pinning, and it's multi-process safe, multi-thread safe. All these buffer objects are first-class objects understood by the Linux kernel. The XRT does address translation because many times the devices don't have MMU and they're directly accessing the memory, their attached memory, but on the host, you're still using virtual addresses. And it's a data-driven memory manager because every time you compile a design, the design may use a completely different topology. You may use 1 DDR versus 4 DDR, and sizes of DDRs might change. So it's a data-driven. We discovered it from xclbin, and then we initialize a memory manager. There are a bunch of APIs. One interesting API you'll see at the very end is called CopyBio. That was a new feature added recently, which leverages DMA engine built into the device for moving data between different DDRs or different banks or on-chip memory to off-chip memory. So it's pretty powerful. And it's a very simplified API for intuitive API for end users. The execution model is asynchronous, which means you just queue up tasks as fast as you can. Maybe one thread, another thread is just waiting for tasks to finish. And the wait is implemented as internally as a POSIX poll. So it's asynchronous. And when you wake up, you go and see how many of my tasks have finished. And how you figure out your tasks are finished is by looking at the same command object that you had submitted to the kernel. So there is a status field there which gets changed to done or aborted or error, so you can monitor your tasks. And the kernel will wake you up whenever it thinks that one or more of your tasks have finished. The command buffer object, as I mentioned, is defined in ERT.h, and it's all open source. If you want, you can look at the data structures. If you're using OpenCL, then you don't worry about these things. It automatically handles these things. You're at like a CLNQ task level. But if you want to write your own application and you want to play with it closely, you can create your own command objects explicitly. I mentioned advanced technology. So one of the advanced technologies that we enabled in 2019.1 is PCI peer-to-peer support, which means if you have a bunch of these devices plugged in onto a PCI bus, you can set up a very interesting pipeline execution across these devices where buffers are shared between these devices. So the peer device is essentially providing you data by directly writing into your device attached memory, and you could be writing in your neighbor's device memory. So all that orchestration is handled by the application by using XRT APIs. Like you can call CopyBio, and that will keep moving data across as you're executing things. One interesting anecdote is if you go on Google and you search for PCI peer-to-peer, the first link that you will get is XRT, as if we are the first ones who made it very popular. And we use it for like our storage devices, storage acceleration devices with NVMe. So I mentioned xclbin in my first slide. That's the binary that is produced by our compiler. And the xclbin is essentially derived from ELF. It has sections for various parts of the FPGA initialization. So things like the bit stream that will configure the bits and the flops and the connections in the FPGA. That's very raw. But then there are sections for memory topology and IP instantiations, like the compute units that you have compiled into your design. They will start showing up in xclbin. And these are well-defined C structures in xclbin.h header file. And XRT ships with this xclbin util tool, command line tool, to explore xclbins, to create xclbins, to change xclbins. In fact, V++ internally uses xclbin util to assemble the xclbin as a binary. So touching upon the XRT command line tool, so we have tools for configuring the device, like flash update the device, so the device itself will update the shell itself will get updated, and we'll look at the shell in a little bit. You want to configure different aspects of the device. As a system administrator, you want to scan for devices. And the xbutil, again, has a whole set of subcommands that are most interesting for end users to query the device, look for its status, and request for a reset. Live top, so when you're running an xbutil top, it'll give you live metrics of the device, how much compute units are being used, how much memory is being used, how much data has transferred, and of course, xclbin util. One interesting thing about Xbutil is the validate is built into Xbutil. So if you plug in an Alveo device today and you run Xbutil validate, it will tell you whether a device is up in a good state, it's running, it's ready for use, and different metrics about DMA bandwidth and other interesting tidbits. Here is how Xbutil query output looks today, or maybe in the last release. And you can see different sections are showing different aspects of the Xbutil. I don't know whether it has a pointer, but anyway. If on the right-hand side, you'll see memory status, so different memory blocks that have been initialized or not initialized because our user application doesn't use them, how much memory is there, how much is being used, how much DMA transfer has happened, what compute units are there. So if you want to see on the right-hand side, on the lower side, you'll see there are 2 compute units there at some addresses and what is their state. So all that in metrics, including the sensor data and all that is live. So it's like an in-band BMC, if you will, for your application, for your device. Okay, cloud support. I have one slide on this which kind of gives you an overview of how XRT implements cloud support. So one thing we realize is that there are many hyperscalers out there which have their own interesting ways of communication between the VM and the host, or whether it's through cloud or whatever, right? It's their own proprietary implementation. So the way XRT supports virtualization is that if you have, we have a 2 physical function device, as I mentioned, and the physical function 0 is a management device which is hidden inside the hypervisor, and the guest VM gets access to the XOCL driver, which is where it's doing all the interesting things. And for communication between the 2 devices or the 2 physical functions, for all control messages, you use the drivers use the mailbox, which is in the hardware. For all bulk transfer of data, like I want to load this xclbin, you would go through what we call is the MPD MST plugins, which is what the vendor can implement. And these are extensible, and you can do it any way you feel like, but it's, again, dependent on how the hyperscaler has set up its infrastructure. So it does provide that framework for making it very pluggable. So the last 10 minutes I want to spend on the security model and the open source engagement. This is a picture of how our platform, Alveo platform, looks today. And the left-hand side is a shell, and the right-hand side is a DFX partition, which is the dynamic function exchange, which is where you load the xclbin. The platform, the shell itself, has some components which are privileged components, only accessible by the management driver, and some are components are only accessible, or actually accessible by both XOCL and the management driver. So things like clock scaling, or we have these firewalls in the path to the role where people are loading their xclbins that protects any rogue binary or a binary which has bugs from crippling the shell itself. So if you're not speaking correct AXI interface, for example, AXI bus language, the firewalls will trap that and protect the shell itself from crashing. So with this model, and this is what we have deployed in cloud, you can try to load any rogue binary into the DFX partition, and you will not crash the host. Your VM might die if you try to do some incorrect DMA operation, for example, but the host is still secure. So the details for this you can find in our GitHub documentation. The link is at the bottom there. So I already talked about the platform aspect of the security. Let's talk about the software aspect of the security, right? So the XRT packages that you download from Xilinx website are signed by Xilinx, and these are RPM Debian packages. The drivers support UEFI secured boot, and if you're running in UEFI secure mode, then only signed xclbins can be loaded by the drivers. Our code is also, we have a continuous integration with Coverity, which is continuously scanning our code as new pull requests arrive on GitHub, so that gives us any code defect alerts. Often the hyperscalers will implement their own custom logic in their MSD to check for xclbin and make sure that it's not rogue. So you can add whatever additional interesting checks, constraints you want to do for the security. We do support multi-tenancy in the sense that you can have multiple trusted processes running on the same VM, and they're all using the same FPGA. Currently, XRT and Xilinx architecture does not allow one FPGA to be shared between multiple VMs. But many VMs, but a VM can have access to many FPGAs. So that was security, and this is the last section of my presentation on open source development model. So since about a year back, we open sourced XRT on GitHub, and it includes both the Linux kernel drivers and the user space library. The user space library is licensed as Apache 2.0, and the kernel drivers are licensed as GPL. The documentation that we follow is also based on the open source model of Sphinx. So if you look at our documentation, you'll immediately feel at home because it just looks like Linux kernel or DK kind of documentation. We are very agile. If you're following our pull request on GitHub, you will see several pull requests arriving every day from within Xilinx, and we also started seeing pull requests from the community that we have incorporated. It's a pretty huge code base now with 72,000 lines of Linux kernel code and about 127,000 lines of user space code. As a company, upstreaming is new for Xilinx, and we are seeking to upstream our drivers into Linux kernel tree. Earlier this year, around summer time frame, we posted our drivers, the XOCL and the XCLMGMT driver source code for comments, and we got a lot of very interesting comments in there, and we want to follow up in the fall with updates to our driver, including documentation on security and the FPGA technology itself. We are also keen to collaborate with all the Linux distros out there, so IBM, Red Hat if you're around, or Canonical if you're around, or Yocto folks, we want to engage with you to see how we can start bundling XRT as a component in your platforms. And again, to stress that XRT uses standard components. We have not tried to reinvent the wheel when there are things that are already present in Linux and the ecosystem. For example, we use FPGA Manager for memory management of the devices. We use DRM Memory Manager, hardware MON integration, DMA buff, extensive sysfs nodes. We do use device trees for all the initialization of the drivers. Our daemons, the MPD MSD that I mentioned, are systemd integrated. The build and delivery is using CMake, RPM Debian packages. We have Yocto recipes published on Xilinx website. And of course, the development model is on GitHub. We don't have two repositories, an inside repository and an outside public-facing repository. There's one repository where all development happens. And we have Travis CI integration today. So in summary, what I would like to say is, as we all saw, it's a very modular acceleration architecture which works across several classes of platforms. XRT abstracts many of the advanced and very complex technologies into very simple API calls. It's an open source, and we want to be part of a vibrant open source community, and we are seeking collaboration with our partners, with open source vendors, and anybody out there who's interested in acceleration technology. So that's all. Any questions?
So do you support resizable bar from sharing perspective?
Resizable bar?
Yeah.
We have support for it in a sense that if you so when you bring up an Alveo device, you plug it in, you would see that it will show up as 256 meg of PCI peer-to-peer memory. Then you run a XBMGMT command, or actually Xbutil command, to resize a bar to the, we sometimes have 64 gig of memory space or 32 gig. It expands that. If Linux supports that, if the rescan works fine, then you're good. Sometimes the rescan doesn't work because there's not enough I/O space for the things to expand. In that case, you have to do a warm reboot, and there's an extensive documentation online. If you go to XRT page and look for P2P, it'll tell you how to do that. So that's how we support it today.
Okay, thank you.
Any other question? Thank you.